Alrighty, good morning everybody, or I guess good evening, probably your time. Today we are going to learn about thermochemistry. I know it's been a long time since we've done some online notes, so let's get back to it. We're going to be talking about thermochemistry. We're going to start out with some review and a small introduction to new material, and we're also going to correct a mistake of mine. So let's start with that correction. So way back in Unit 4, we were introduced to the idea of heat in the form of Q equals mc delta T. And I called this Hess's law. This isn't actually correct. I know, shocker, right? I'm human and I make mistakes. Q equals mc delta T is an equation for heat, but it is not actually Hess's law. We're going to be learning about the real Hess's law in this unit. Now, I realized about halfway through teaching you about Q equals mc delta T that it wasn't actually called Hess's law and that I'd swapped two equations, but I didn't want to confuse you guys and change things up in the middle of teaching you a topic, so I decided to make the correction when it came time to actually make the correction, which is now, so we're going to do that now. Everything you did learn about Q equals mc delta T is still correct. The name is just wrong. There is actually no real name for that equation. So Q equals mc delta T is an equation we use for heating and cooling curves. It's not actually Hess's law. It's the heat equation, I guess is what you could call it if you wanted to. So, I'm sorry, I hope that doesn't confuse you too much. And let's get to it. So, thermochemistry. Thermochemistry is the study of energy changes occurring during chemical reactions and changes in state. Every substance has an amount of energy stored inside of it. This energy stored in the chemical bonds of a substance is called the chemical potential energy. And during a chemical reaction, a substance is transformed into another substance with a different amount of chemical potential energy. Excess chemical potential energy is then transformed into work, heat transfer, or a combination of both. So thermochem is all about the chemical potential energy stored in each substance. So let's talk about kinetic versus potential energy. So you have kinetic energy and you have potential energy. Kinetic energy is energy due to movement, whereas potential energy is energy stored in an object or a substance or whatever you want to call it. Kinetic energy is released due to movement, whereas potential energy is released under the right conditions. So these are two very different types of energy. Potential energy is often thought of as energy that has potential, meaning it's not there yet, but it has the potential to be there, which is why it's stored in an object, whereas kinetic energy is constantly there. If an object is moving, it has kinetic energy. So let's talk about heat then. Heat, which is represented by the letter Q, is the energy that is transferred from one object to another due to a difference in temperature. Heat always flows from the warmer object to the cooler object, much like in biology when you learn about diffusion and you're going from concentrated solutions to unconcentrated solutions. Here we're going from warmer objects to cooler objects. And if the two objects are touching, energy will continue to transfer from the warmer object to the cooler object until the two objects have the same temperature, or are in what we call thermoequilibrium, or equilibrium of temperature. Sorry, you guys may need to pause and go by pretty quick because there's a lot to cover. So let's look at the difference between heat and temperature. So heat is an extensive property, whereas temperature is an intensive property. And because heat is an extensive property, it means it's dependent on the amount. So it is dependent on the amount of a substance, whereas temperature is independent of amount. And then heat is energy transfer from hot to cold, whereas temperature is just the temperature of an object, so how hot it is. Heat is energy, temperature is actual feel of warm or cold. Okay? So heat is the transfer of energy, temperature is just the temperature of an object. We often confuse heat and temperature, but heat is energy, or energy transfer. Okay. So let's talk about some key terminology that's going to come up in our discussion of thermochem. You have the system, and this is the part of the universe on which you focus your attention. So this is the actual reaction that we're looking at. And then you have the surroundings, and this is the rest of the universe, or more specifically, the region in the immediate vicinity of the system. So when you have the system and the surroundings, you have the entire universe. The system is the very specific part of the universe on which you're focusing your attention, so it's the actual reaction. And then the surroundings is the region in the immediate vicinity of the system, so it's a lot bigger part of it. We can have exothermic processes, which release heat to the environment, to the surroundings. And then you have endothermic processes, which absorb heat from the surroundings. So exothermic processes release heat to the surroundings, endothermic processes absorb heat from the surroundings. So let's do a little recap on specific heat and utilizing Q equals mc delta T. So the specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And we normally represent this by Q equals mc delta T, or more specifically, Q surroundings equals mc delta T. And the reason I'm saying Q of the surroundings is because whenever we're measuring data, we normally aren't actually measuring the data of the system, because the system is a very small part. We're normally actually measuring data from the surroundings. So that's why we say Q of the surroundings. So substances with low specific heats are much more affected by heat than those with high specific heat. So things that conduct heat or electricity well have low specific heats, meaning metals. So they have low specific heats because they're much more affected by heat than those with high specific heats. And things that require a lot of heat to warm up have high specific heats, like water or wood. Calorimetry is the specific measurement of the heat flow into or out of a system. So just a reminder on some terminology there. When we're looking at specific heat, we usually are doing calorimetry or calometric measurements or experiments. And again, this is just a reminder that the heat released by the system is equal to the heat absorbed by the surroundings. Energy cannot be created or destroyed, so if we're losing heat by the system, it has to equal the heat absorbed by the surroundings. Now, that heat doesn't always have to be in the same form. It doesn't all have to be temperature. It could be light or, light or vibration or many other things. So let's talk about enthalpy, or it's represented by the letter H, and that's a lot about what thermochemistry is. We're going to talk a lot about enthalpy, or enthalpy change. Enthalpy is the heat content of a system at constant pressure. So the heat absorbed or released by a reaction at constant pressure is the same as the change in enthalpy, or delta H. So what we're going to mostly be looking at here is the change in enthalpy, or the heat absorbed or released by a reaction, because almost all reactions occur at constant pressure. It'd have to be a very special situation or circumstance for it not to. So we're going to always be looking at the enthalpy, the heat absorbed or released, and that equals the change in enthalpy. Exothermic reactions have a negative enthalpy, or a negative change in enthalpy, a negative delta H, because they're releasing heat from the system into the surroundings. And endothermic reactions have a positive delta H because they are absorbing heat from the surroundings into the system. Because of this, because the system and the surroundings equal the universe, Q system has to be equal to negative Q surroundings. It's the whole idea of energy being conserved, and the energy lost by the system is gained by the surroundings. We can also represent this by saying that Q system is equal to delta H, which is equal to negative Q surroundings, and Q surroundings is equal to mc delta T, so that equals negative mc delta T. Q systems and Q surroundings and delta H is, oh my, that's a lot of confusing terminology, so let's take a look at it and figure out how these are, some of them wind up being negative. Experimentally, we measure Q surrounding as measuring the Q, so experimentally we measure the Q of the surroundings, like I said, because measuring the Q of the system is incredibly difficult. It's a very small part of the universe. So then delta H, however, is always calculated in terms of Q system, as the heat of enthalpy is of the system, not the surroundings. Because of this, since we normally calculate Q system when we're calculating delta H, we need to actually calculate negative Q surrounding, as Q system is equal to negative Q surrounding. So that's why delta H will be negative for an exothermic reaction and positive for an endothermic reaction, because we're looking at the negative Q of the surroundings. Okay? Take a minute to read over that again and again and try and connect that in your head. We'll be talking about it in class too. Alright, so let's practice this. When 25 milliliters of water containing 0.025 moles of hydrochloric acid at 25 degrees Celsius is added to 25 milliliters of water containing 0.025 moles of sodium hydroxide at 25 degrees Celsius in a calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during the reaction if the final temperature is 32 degrees Celsius. Assume the density and specific heat of both solutions is 1 gram per mil and 4.18 joules per gram degree Celsius, respectively. Okay, so let's look at how we're going to do this. We know that Q system is equal to delta H, which is equal to negative MC delta T. So our delta H is going to be equal to negative MC delta T, which means that we're going to have negative 25 plus 25, because we had two different masses of water, multiplied by the specific heat of both solutions, which is 4.18, multiplied by the change in temperature, or 32 minus 25 degrees Celsius. That gives us an answer in joules, but they asked for an answer in kilojoules. So that gives us delta H is equal to negative 1.46 kilojoules. Okay. We have a negative delta H, which means that this was an exothermic reaction. Alright, so now let's look at chemical reactions and enthalpy change. In chemical reactions, enthalpy change can be written as either a product or a reactant, dependent upon if the reaction is exothermic or endothermic. If the reaction is exothermic, our enthalpy change is a product. If it's endothermic, it's a reactant, meaning heat was either given off, so it's a product in exothermic, or required as a reactant in endothermic. So for example, calcium oxide plus water making calcium hydroxide gives off energy. So the enthalpy change is a product, which means that when you write it as a change in enthalpy, it'll be negative 65.2 kilojoules. So let's practice. If you've been given this equation, 2 sodium hydrogen carbonate plus a certain amount of energy making sodium carbonate plus water plus carbon dioxide, you could also write this as have it as 2 sodium hydrogen carbonate making sodium carbonate plus water plus carbon dioxide having a delta H of 129 kilojoules, meaning it's an endothermic reaction. Given the reaction above, what is the enthalpy change for 2.75 moles of sodium hydrogen carbonate? So our delta H is going to be equal to the number of moles, because this delta H here, the 129 kilojoules, is 129 kilojoules as this reaction is written. Which, if everyone remembers back when we were writing chemical reactions, these numbers in front are numbers of moles. So we have 2 moles of sodium hydrogen carbonate in this reaction, but what if we had 2.75 moles? So we're going to start then to figure out our answer with 2.75 moles, and we know that for every 2 moles of sodium hydrogen carbonate, you get 129 kilojoules. So if we multiply all that together, we get 177.375, or 177 kilojoules if we keep sig figs constant. So nothing too mind-blowing. Let's look about it in terms of changes of state. So remember way back when we were doing the heating and cooling curves, we talked about solid, liquid, and vapor and the different phase changes. Well, vapor has a high enthalpy and solids have a low enthalpy. So when you're going from a solid to a liquid, you have a positive delta H of fusion. When you're going from a liquid to a vapor, you have a positive delta H of vaporization. It should make sense that these are positive, because that means that it's an endothermic reaction, meaning you need to put heat into the system, which you do have to heat up a solid to melt it, and you have to heat up a liquid to boil it. Whereas vaporization to liquid or condensation is a negative delta H, and solidification, liquid to solid, is a negative delta H or solidification, because you're losing energy because it's solidifying. So that should all kind of make sense. The molar heat of phase changes is the amount of heat absorbed or lost by 1 mole of a substance as it changes phases. Because it is for 1 mole of a substance, the units are always kilojoules per mole. So let's look at a phase change calculation. We can use these standard heats of phase changes to calculate different things: the amount of heat required to perform a phase change, the grams of a substance that will melt given a specific amount of heat, etc. So my question then is, how many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat is added? given that the delta H of fusion is 6.01 kilojoules per mole, and water has a molecular weight of 18.05 grams per mole. So first off, we have to write our equation that solid ice plus our delta H of fusion equals liquid water. Then we look at the mass of ice, or the mass of ice would be equal to our single unit of 2.25 kilojoules multiplied by 6.01 kilojoules for every 1 mole of ice multiplied by the moles per gram of ice gives you a total of 6.74 grams of ice. So that's how much ice will melt if you add 2.25 kilojoules of heat. So we've done heats of phase changes. Now let's look at heats of solution. During the formation of a solution, heat is either released or absorbed. The enthalpy change is called the molar heat of solution and is representative of the heat released or absorbed caused by the dissolution of 1 mole of a substance. So dissolving 1 mole of a substance in water. This is the reaction that is occurring in disposable hot or cold packs, where hot packs are formed from an exothermic reaction and cold packs are formed from an endothermic reaction. So when you're cracking those, you're actually breaking open a substance and dissolving it into the solution, and that creates an endothermic reaction for cold packs or an exothermic reaction for hot packs. Okay, so we're going to get more into actual Hess's law in class tomorrow, but I just wanted to kind of give a brief overview of the stuff that we learned about heat and introduce you to some new ideas of like the heats of solution and heats of phase changes for now. So I will see you in class tomorrow.